Hello and welcome to this lecture. So, now that we know how to identify diagonalizable matrices, and whenever we identify diagonalizable matrices, we know how to find that S such that diagonal equals S inverse AS, right. So, we know how to do that. So, what use can that be? What use can we put it to? So, we will see a lot of interesting uses for such things. First thing is powers of a diagonalizable matrix. When you have an n by n matrix, sometimes you are interested in powers of A. Okay, a power m, a squared, a cube, a power 4. Is there an easy expression, particularly as m goes large? What is a power m? Very often we are interested in that. Many applications have that. I think in the 2 by 2 case, I motivated why you might need it. But these powers of a matrix are very, very important. Recursive equation solutions are very important. So, now if A is diagonalizable, there is an invertible S such that diagonal matrix is S inverse AS is D1 to Dn. This is diagonal, right? Now, this S inverse AS has a special name. It is called a similarity transform. The reason is, when you do S inverse AS, you are just getting another matrix for the same operator, right. A is one operator, A is a matrix of one operator, right. For the same operator, this S inverse AS is another matrix, but with the basis which is columns of S, right. That is the way to think about it. So, this S inverse AS is similarity transform. It is interesting because A represents an operator, S inverse AS also represents the same operator and another basis. What is that basis? Columns of S. Okay. S is invertible, so columns of S form a basis. Okay. So, this is called a similarity transform. Now, the point of most useful thing about similarity transform, one of the most useful things about similarity transform is when I do D squared, I simply get S inverse A square S, and that is just D square is very easy, right. I square the diagonal elements. Okay. Same thing can be pushed. Any power of D is actually very simply in a similarity transform related to S inverse A power ms, because this S inverse will always cancel in the middle. You will only be left with the S inverse on the left side and S on the right side. Now, this D power m is very easy. It is D1 power m to Dn power m. Okay. So, now you can push the S's to the other side. Okay. So, you can push the S's to the other side. What do? I multiply both sides with S. So, I will get S D power m on this side. I multiply on the right with S inverse. So, my A power m becomes S D power m S inverse. Now, this is just a diagonal matrix. Power is very, very easy. So, once you have a diagonalizability, for a matrix, finding arbitrary powers of the matrix become very, very easy to do. So, here are specific examples. Okay. So, you will see here you have a matrix here. So, you may be able to find all the eigen values here, and in fact, all three cases you can find the eigenvalues, and from there you can go on to check whether A power n, how does it behave as n tends to infinity. Okay. So, just off the top of my head, I will tell you this guy, as you go to larger and larger n, this will go to a constant matrix. Okay. So, you may be surprised, constant rank 1 matrix. This will blow up, this will go off to infinity if I am not wrong, okay, in a specific way. This will go to 0. Okay. So, all these things you might be mystified by. It's got to do with the values on the diagonal, right. Everything has got to do with the values on the diagonal. If any of these values on the D1 to Dn, if any of them are greater than 1, then the D power m will blow up, right. It will go off to infinity. If all of these guys are less than 1, okay, then it will go to 0. Okay. If only one of them is 1 and everything else, or a few of them are 1, everything else is less than 1, then it will go to a constant. So, it just depends on the magnitude of the eigenvalues. Okay. So, I will urge you to try this very closely. Maybe we will try just one to see how that behaves, and maybe I will try the first one just to show you how that goes to a constant 0.3, 0.4, 0.3, 0.4, 0.4, 0.2 and 0.3, 0.2, 0.5. Okay. Let us try that. The matrix is 0.3. Okay, I should go back and look at it. 0.3, 0.4, 0.2, 0.3. Sorry, I think it's sort of symmetric. I think this is what it is. Let me just check once again. Yeah, okay. So, now my eigenvalues are going to be 0.3 minus lambda. So, this is a bit of a pain, right. So, 0.3 minus lambda, and the diagonal will come out here, minus 0.04 minus 0.4 into 0.4 into 0.5 is 0.02. Oh no, did I get that right? 0.4 into 0.5 is 0.20, sorry, minus 0.3 times 0.4 minus lambda, and then you have a plus 0.3 times 0.4 into 0.2, which is 0.08. I'm sorry, I got that right. Did I get it right? Yeah, this one 0.4 is 0.08 minus I think I got it wrong here, right? So I think something is wrong here. 0.4 is 0.4 into, that's what I got wrong, 0.4 into 0.5 minus lambda minus 0.06. Last guy is 0.08 minus 0.3 into 0.4 minus lambda. Okay, this equals 0. It looks like a complicated mess, and it is a little bit. So, so I'm going to argue here. I'm going to cut to the chase a little bit. I know it's a bit boring, but this is what it is. So lambda is going to be 1. Okay, one of the lambdas will be 1. Okay, how do I know it? I know it for some special reason. In fact, the eigenvector corresponding to this is 1, 1, 1. Okay, the eigenvector is actually 1, 1, 1. You can check this. You might take this matrix and multiply by 1, 1, 1 on the right. When you multiply it, it's a sum of the rows, right? So if you look at the sum of the rows, you get 1 here, 1 here, 1 here. Okay, so it just becomes 1 into 1, 1, 1. So 1, 1, 1 is an eigenvector with eigenvalue 1. The other two are going to be absolute value less than 1. Less than 1 in absolute value. Okay, this one will also be less than 1 in absolute value. Okay, these two in absolute value will be less than 1. This will be just 1. Okay, so what does that mean? This matrix, there is an S such that it becomes 1, 0, 0, 0, something that is less than 1. Okay, 0. Let me write it as D2, 0, 0, D3. What do I know about D2 and D3? Absolute value of D2 is less than 1, absolute value of D3 is less than 1. Okay, times S. And what is this S? This S is 1, 1, 1 in the first guy and something. I don't know what it is. I'll just put a star. I don't even know what it is, right? So, what will happen if this is my D, right? What will happen if I raise A to the very large power? I'm going to get S inverse D power M. 1 power M will remain the same. I'll get D2 power M, D3 power M times S. Now, D2 power M will tend to 0, D3 power M will tend to 0. So, as M tends to infinity, A power M, I'm sorry, will tend to, right. So, S inverse times 1, 0, 0, 0, 0, 0, 0, 0, 0 times S. Okay. Now, what is 1, 0, 0, 0, 0, 0 times S if you multiply? Now, S is what? S is just 1, 1, 1, star, 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 star. Okay. So, only the first row here will remain, everything else will go off to 0, right. So, you will get only the first row and everything else will go off to 0. So, it's an easy thing to calculate. If you want, you can calculate it. If you know S inverse also precisely, if you know these cases precisely, you can find it out. It's just 1, 0, 0, 1, 0, 0, 0. Only the first column here will matter, and then the first column will multiply the first row and you get an answer. Okay. So, you can see this A power M will tend to some sort of a constant. I don't know what that is, but that's what it will tend to. Okay. So, hopefully you can see this. If you do it very carefully, you will get to the answer. Likewise, here you will get you can see that 101, the vector 101 is an eigenvector with eigenvalue 2. So, there is an eigenvalue 2 there. So, that will show up on the diagonal and it will go 2 power m. So, it will start blowing up. Okay. And likewise here, if you see 0.9111 is an eigenvector with eigenvalue 0.9. So, if you multiply 111, all the row sums are 0.9. So, and every other things are less than that, I think. Okay. So, once you get that, the 0.9 power m, that will itself will tend to 0. So, everything will tend to 0. You will get all 0 here. Okay. So, I'll urge you to check it out carefully and then convince yourself that finding powers of a matrix is very easy when the matrix is diagonalizable. Okay, thank you.